Hi everyone, today we're going to talk about the elastic potential energy and conservation of energy, and we'll go through a couple of examples. The goals for this video are I will be able to calculate the elastic potential energy of the system, and I'll be able to apply conservation of energy to open and closed systems. As we've talked before, potential energy is a stored energy due to the position of the system, the object, and we talked about the gravitational potential energy. However, there is another type of potential energy, which is called elastic potential energy. It occurs in springs and other restorative objects, such as rubber bands. We'll mostly deal with springs in this course. And the energy, elastic potential energy, US, as it's notated in your reference sheet, equals to 1/2 K x squared. K is the spring constant. It is a property of the spring, and it just represents how difficult it is to stretch the spring. If it's a low K, it is easy to stretch the spring, and if it's a large K, it is very difficult to stretch the spring. And x is a displacement from equilibrium, this x. So another notation for the elastic potential energy that we will be using is PE subscript S. So we can differentiate it from the potential gravitation potential energy, which is PE. So as a result, our work energy theorem, the general equation for the theorem will look like that the work done by non-conservative forces on the system equals the change of kinetic energy, change of gravitational potential energy, and the change of elastic potential energy. Sometimes very often we will not going to have all three kinds. It's just a general equation that we should keep in mind. So open and closed systems. So for all systems under all circumstances, energy, charge, linear momentum, we will learn it later in the course, angular momentum, those quantities are conserved. An open system is one that exchanges any conserved quantity with its surrounding. So we'll make sense of it with examples later on, but just this is a general definition. So if that doesn't happen, it is a closed system. So conservation of total mechanical energy. When we have a system where the only work being done is by the force of gravity of springs, we can say that the total mechanical energy is conserved. And it makes sense because we know that the force of gravity and the spring, the force that acts on springs, is both are conservative forces because they can be restored back, right? Whereas the non-conservative forces such as friction cannot be restored back. We cannot get back the energy from those forces. So this is an example of a closed system where total mechanical energy is conserved. So total potential energy plus kinetic energy remains constant. For example, in this motion of a person on a bike, where the person is not pedaling on the bike is just skidding up the hill and down the hill. So it will slow down as it's going down because the kinetic energy is decreasing as potential energy is increasing, and vice versa. Another example is a roller coaster. When we assume that the friction is negligible, we can say it's another example of a closed system because there is no non-conservative forces acting on the system. Therefore, total mechanical energy is conserved. So in this case, we do not have the elastic potential energy. So the only energy we have is the kinetic and gravitational potential energies. So those two energies are conserved. So initial position, for example, if it has a high potential gravitational potential energy and low kinetic or even zero kinetic in the beginning, the sum of those will be constant throughout the ride. So this position will decrease the potential energy but increase kinetic, and this position will decrease kinetic relative to this position and increase potential energy. Let's look at this example. We're going to solve. We have a toy propels a 0.3 kilogram ball into the air using a spring. The spring is compressed 0.02 meters before it is released. Calculate the height reached by the ball if the spring constant equals, first case 4,000 newtons per meter and second case 8,000 newtons per meter. So let's look at our sketch here. Here's the spring compressed. Y initial is the vertical distance from the equilibrium position. This is the equilibrium position right here, which is the reference point for the gravitational potential energy. And that is the H max that we need to find. What's the maximum height above the toy, above the reference point that the ball will go. So we write the work energy theorem. Work of non-conservative forces in this case equals to 0, and it equals the initial energy. So the total energy is conserved. So initial energy equals the final total mechanical energy. So the conservation of energy can be applied to this situation because the system is a closed system. So here's our initial energy. We just write the all three possible kind of energy that the system can have, which is kinetic energy, gravitational potential energy, and elastic potential energy. And then it should be equal to all those three in final position. Again, our initial position is when the ball is compressed, and final position when the ball reaches its highest point. So let's think which energy is equal to 0, because have some energies that are equal to 0. So when the ball is compressed, the kinetic energy is 0. We have potential energy, which will be negative relative to the reference point. Remember, we put this in class, and initial by initial. And we have elastic potential energy, and at the final position, we do not have kinetic energy, the ball is not moving at the highest point. Then we do have gravitational potential energy, we do not have elastic potential energy in the highest point. So it simplifies our life a lot. So that's the equation we have for the conservation of energy. Now we can do some algebraic manipulations, and we can find that maximum height will be equal to potential energy initial plus elastic potential energy initial divided by the mg. And when we calculate when we plug in the numerical values, we can calculate the height. Be careful when you're plugging in the initial position relative to the reference point, it should be negative. So it is a negative number, as well as the x for the elastic potential energy. However, for the elastic potential energy, it doesn't really matter because it is going to be squared, so it is not going to make energy negative. So elastic potential energy is always positive. So we can calculate, and we can find that the height is going to be 0.25 meters, which is 25 centimeters. So next question is asking us what is it going to be if we double the k, if we double the spring constant. So let's do some prediction here. This is our equation. We can say that if k will double, and this quantity is very small, we can assume that the height will be approximately double because there is linear dependence. But let's check our prediction. Let's look at the calculation here. So we use the same formula, but we double the k, and when we plug in all the numbers, yes, we can see that it is about double. So it's half a meter in this case. So our next question is asking what is going to happen if we have a different compression distance, not 0.02 meters, but 0.04 meters. Okay, that's our other question we have. So that's the new question we have. If the same toy is now compressed 0.04 meters, calculate the height reached by the ball if the spring constant is 4,000 newtons per meter, and calculate the speed of the ball as it leaves the toy. So let's look at our formula for the maximum height. This time we have a different compression number, 0.04 meters, and plugging it the values, we can see that the height is about 1 meter, and it about 4 times the original height we calculated in the previous examples, right? The 0.25 times 4 is 1 meter. Does it make sense? Well, we doubled the compression distance, and then we quadrupled the height, and it makes sense because the compression distance, square of compression distance, is proportional to the height. The next question is whether what's the speed when the ball is at the reference level, at the reference position, what's the speed of the ball. So in this case, we have to define what our positions are. Initial position is a compressed state, and final position at y, the reference point, is 0. So again, we don't have non-conservative forces acting on the system. It's a closed system. The initial energy, total mechanical energy, is conserved. So initial energy equals to final energy. So again, all 3 kinds of energies are our general statement. And usually some of the energies will be equal to 0. So in our case, when the spring is compressed, the ball is not moving, so kinetic energy initial equals to 0. We have this 2 though, and the final position, the ball is moving, but we do not have gravitational potential energy because it's at the 0 at the reference point, and we do not have the elastic potential energy because the delta x is 0. So we have this equation, much simpler, and then just do some algebraic manipulation, multiply all terms by 2, find the final velocity, which is this formula, kx squared plus 2mgy initial divided by m. So when you plug in all the numbers, you get velocity equals 4.53 meters per second. Okay, now our last example is the example of an open system where work being done by forces other than gravity or springs, and the total mechanical energy is not conserved. So that's the simplified work energy theorem for that case, but we can use our general equation as well. But let's look at this example. We have a 2,500 kilogram car, starts from rest at the top of a 5-meter long driveway that is inclined degrees with the horizontal. If an average friction force of 4,000 newtons impedes the motion, find the speed of the car at the bottom of the driveway. So let's look at our sketch of the problem here. We have a car, it's going down the incline. We know the length of the incline, L, which is 5 meters. We know the angle, which is 20 degrees. And we know the mass of the car and the force of friction, which is opposite to the motion. So we need to find the final velocity of the car at the bottom of the incline. Let's write our equation. So work of non-conservative forces equals change of total mechanical energy. This is an open system, right? So work of non-conservative forces is not equal to 0. The work of friction. So change of mechanical energy is the change of kinetic final minus kinetic initial plus change of potential energy, potential final minus potential initial. So we don't have elastic potential energy, we only have gravitational energy in this case. So let's think which energy equals to 0. So kinetic energy initial equals to 0 because the car at the top of the incline does not move, and potential energy, gravitational potential energy equals to 0 because the car the reference level is at the end of the coarse motion. So we can rewrite the work of friction as force of friction multiplied by the displacement and by the cosine between those two. That's why I didn't write theta, so you do not confuse it with the inclined plane, but I just wrote alpha, which is 180 degrees, the angle between those two. And it equals the kinetic energy final minus gravitational potential energy initial. Okay, so let's keep work. We rewrite what the work force of friction multiplied by the length of the path times cosine 180 equals 1/2 mv final squared minus mgh. So h, if we look at our sketch, we can find h if we know the angle and the length. From the right triangle, h is going to be L multiplied by sine of 20 degrees. That's what we do here. And after we do that, we can continue with our equation. And then after we continue with our equation, we can solve it. We can solve it like this. Okay, we can find the final velocity and we can plug in the numbers and we can find that final velocity is 3.89 meters per second. Okay, so that was an example of the system.